welcome to our next speaker, Martin Pecka. Martin is the researcher at Vision for Robotics and Autonomous Systems Group of Czech Technical University in Prague.
Yeah, and then his presentation is about how to clean point clouds. You know that point clouds, we are generating point clouds with our RGBD cameras, and we use this to detect obstacles, to identify objects, and so on. But if you put a RGBD camera on top of a robot, and then this robot is moving in very hazardous ways, then maybe your point cloud is going to be messed a little bit with a lot of spurious data on it. So Martin is going to show us how we can clean those messed up or dirty point clouds so we can take the most of the information contained on them. Hello, Martin. Are you ready?
Yeah. Hello.
Hello. Perfect. So the audience is all yours.
Okay. Thank you. So let me welcome you. I'm Martin Pecka from Czech Technical University in Prague. And this talk will be about how to clean point clouds. So basically, many of you have probably worked with some 3D sensors like either RGBD cameras or LiDARs. And if you mount the sensor on a body of the robot, it might happen that the sensor sees the body of the robot. And that's usually not what you want, because if you want, for example, to build a map from the data that you collected, the body of the robot should definitely not be in the map. So this talk will be about how to get the body of the robot out of the point clouds and keep just the points that represent the map that you are building or the environment. So let's take it slowly and from the beginning. So all of the functionality that's needed for cleaning the robot body from the point clouds is contained in the robot body filter package. And you can try it in the ROSDevDay here, or you can also try it on your own computer. So this talk will use ROS Melodic as the base. And what is maybe a little bit unusual here, for simulation, we don't use Gazebo Classic, but we use Ignition Gazebo, the next generation Gazebo. And in particular, we use the DARPA Sub-T simulator, which is something built on top of Ignition Gazebo. And it is a simulator built for a competition organized by DARPA. For example, here is an image from the simulator. The competition is about exploring underground spaces with a fleet of robots as autonomously as you can. So the competition has now been running. It's entering the final stage. And as we are preparing for the competition, we need to use our robots in a way that they can navigate in the underground spaces and they can precisely map, because precise localization is one of the key aspects of the competition. If you don't want to install the Sub-T simulator because it might be resource hungry, I also prepared back files. So you can just download back files and repeat all the steps we will do here on the back files. The only problem is that the back files are quite large as they contain 3D sensor data. So it's not possible to download them in the ROSDevDay, in the cloud simulation. But if you're running locally, just append this Gazebo. There is a way to run it. It should be a parameter Gazebo equals false. And if you append it to any command, it will try to download the back file corresponding to the scene that we will be working with. And that will be it. Yeah, the parameter is here, Gazebo equals false. Another thing you need is the robot body filter package. You can normally get it via apt-get installing as a normal ROS package. But for this speech, we will use some features that are not yet released. They are contained in a branch that's called perlink scaling. So if you just want to try it out locally, don't forget to clone the robot body filter package from GitHub and switch to the branch perlink scaling. All the other code that I will present you here is in Catkin WS, SRC, ROSDevDay cloud filtering. So if you look here, there are mostly launch files that we will use. And these launch files usually launch a simulation of one of the robots and set up the robot filter. So let's jump in. Let's see how exactly does it look when you have a robot and its point cloud is not filtered. So I'll just start the simulation of a husky robot, which is a pretty simple. Many of you probably know it from ClearPath, a four-wheeled robot. And this one has a payload designed by our team, which contains a 3D LiDAR. So if you just run this command in terminal and open the visualization tools, you will see an instance of gazebo starting and an ROS. And in the ROS, you can see the robot. And we have nothing here, which means the gazebo crashed. That's something that happens to the ignition gazebo sometimes. That I think, old gazebo crashed also, but the ignition gazebo, I would say, has even more crashes. But on the other hand, we are able to run like 24-hour simulations, so it's not that bad. It's just unpredictable. So yeah, here you can see the interface of ignition gazebo with the husky robot spawned. And here we have the husky in ROS. And we can enable this LiDAR original point cloud, which shows us exactly the points on the robot that are captured by the simulated sensor. And as you can see, these points captured on the payload itself are the points that we want to get rid of, because they should definitely be part of a map. So how do we do it? There are several ways how we can get rid of such points. And the simplest one, many of you probably know, would be, okay, so all simulated sensors have some like minimum range configuration. So let's just increase the minimum range of the LiDAR so that it doesn't see the payload. But that's not really good, because if you would, for example, set the minimum distance so that the robot, I don't know, this could be like 0.5 meter behind. So the minimum distance set to 0.5 meter would also mean that you would lose some obstacles that would be in front of the robot, 0.5 meter and less. So this is definitely not something we would like to do in this situation. Okay, so what's better? Basically, setting minimum distance is cutting out a sphere from the point cloud. It could happen that cutting out the box instead of a sphere would be better. So I've put here a simple configuration of PCL crop box filter, which is exactly the filter that takes a point cloud and cuts out a box out of that point cloud. So if you just copy this configuration and run a second node, it will start the filter. And now in the ROS, we should have 2 point clouds available. One is the LiDAR original, and the other is the LiDAR filtered, the green one. And you can see, okay, yeah, we got rid of that points. There's nothing on the payload now, and the point cloud looks as we would like it to look. But still, this is not perfect because the box that we use is centered in the lidar and not in the middle of the robot. And as you can see here, the lidar is in the front. So like using any kind of box that is centered around the lidar is kind of weird. It's not really, you know, representing the reality. Fortunately, you can specify the center of the box even to the crop box filter from PCL. So here is another command which just added the parameter that we want to filter in frame. That's called X1. Here in sub-T simulator, we call the robots X1, X2, X3. So X1 is something that corresponds to the more known base length frame. So I just specify that I want to do the filtering in X1 frame. And that's it. You know, the point cloud looks the same, but now I know that I actually filter the point cloud by a box that is centered in the middle of the robot and just encloses the body of the robot quite closely. So this is good. I think for Husky, we could end here and it would work. But as we want to talk about robot body filter, let's see how we would do the filtering with robot body filter. So let me first stop both nodes that I have launched, even the simulator. And, sorry, I should not have stopped the simulator. Here is a command line that launches a super simple sensor filtering chain. So basically, you know, probably nodes, you know, nodelets, and filters is like the third, not that much very known concept of ROS. Filters are something that's connected in filter chains. So there is an input message that is put into the filter chain. Then there is a chain of filters that work on the message. And at the end, there is the output of the filter chain. So basically, it's just the messages being passed through a chain of something that modifies the point clouds or messages in general. And so now we have the simulator running again. And in the second console, I will launch this sensor filters point cloud 2 filter chain, just an empty chain of filters. And as you can see, the empty chain of filters, of course, does not do anything to the point cloud. But as I have redirected output, the X1 points filtered, we now have the output of the filter chain available as the lidar filtered point cloud. You can see that the points we wanted to get rid of are still there. So let's put there some configuration of the filter. And that is usually done in a YAML file that configures the filters. So you have a node that's usually called cloud filter chain or something similar. And then there is a list of filters that should work on the point clouds. In this case, we have just a single filter, the robot body filter. The first two lines are just configuration telling that the robot body filter should be used. And then there are a few parameters that you need to set correctly. The most important one is the filtering frame, which is, you know, the point clouds can come in any frames. And you might want to do the filtering in some different frame. So basically, the filtering frame is the frame into which the point clouds are transformed. Then the filter is applied, and then they're transformed again to the output frame. You do not need to set the output frame. If you do not, then the point cloud will have the filtering frame. Then you have the usual max and min distance of the sensor. You can set it as you like. This is basically cutting out the sphere. So I recommend setting these parameters to not work on the point cloud that much because you are usually already limited by the physics of the sensor. So these parameters should generally just copy the physics of the sensor. And then important parameters, inflation. So to filter the points from the body of the robot, we know that any sensor measurement is biased by some error, and so that the points that lie on the body of the robot do not actually need to lie exactly inside. They might be like 2 millimeters above the robot body. So to filter these points out, we inflate, scale the robot body, and the amount of scaling is specified by these two parameters. So scaling means that you just, multiply the scale of the robot by 1.1, and padding is in meters, and it means that after you apply the scaling, you should add 2 centimeters to every collision element of the robot. It's up to you whether you prefer scaling or padding. Sometimes it's better to scale, sometimes it's better to pad. It depends on the size of your links. And one important setting here is the do shadow test. For now, we set it to false because we will talk about the shadow filter later. Yeah, and this is how we launch it. So basically, this is just a launch file version of the command I have launched in the console. It's just starting the sensor filters, Pointclouds to filter chain node, and loading the configuration. This file that we have created, the husky simple YAML, you load it inside the node, and this configures the filter chain. And then, of course, you remap the topics from input output to wherever your point clouds are. So let me now stop both terminals, and I will restart the simulator with the robot body filter applied already. So that's done by the husky simple.launch. And it will, again, launch the simulator, the ROS, and it will also launch this laser filter configuration. So let's see what happens. And if we wait for a while, we should start seeing the output of the filter. Yeah, so now, again, we are displaying the LiDAR filtered already, and you can see it's again what we wanted. So there are no points on the payload and just the points in the map. Perfect. But there is one thing. As you might remember, we set the scaling to 10% and added 2 centimeters in every direction. And we can actually visualize what it does to the robot model. So robot body filter publishes these debugging helpers, and one of them is the model of the robot that's actually used for the filtering. It's based on the collision model, not the visual model, but on the collision model of the robot. And here you can see that it somehow corresponds to the 10% scaling and adding some 2 centimeters to every direction. So yeah, you might say this is okay for me, or you might say, oh, this is still a little bit too large. I might be interested, for example, in the points in front of the bumper. So I would like to get tighter. Okay, so let's get tighter. We can configure the filter even more. We can decrease the scaling from 10% to 1%. And the problem was mostly with the top link with the sensor rack. So let's say, okay, generally all links should be scaled by 1%, but the X1 sensor rack collision top should be scaled by 20%. This is how you record this kind of configuration. So there is a per link scale config, and then you put here the name of the collision that you want to scale differently. The collision is read from the URDF description of the robot. So X1/sensor rack is the name of a link. That's the link that's representing the whole top of the robot in this example. And collision top is the name of the collision element. In the URDF, you will see these collision elements, collision name equals, and inside is the geometry of the collision. And some of them may have the names. In this example, it's named collision top. So you say, okay, so I want the collision top element of X1 sensor rack link to be scaled by 20%. Okay, that's good. And what if the collision doesn't have a name? That also happens. In case you need to mention a collision that doesn't have a name, you can just index them from 0 to whatever the number of collisions per link is. Okay, so now we have a better configuration, or at least I hope so. And here are a few more configurations for debugging. You know, if you are setting the filter for the first time, you might want to verify a lot of stuff. And this is what helps being sure that you did it correctly. So we enabled, for example, the debug marker contains, which is exactly this marker that shows us the model used for filtering. You can find description of all these debug helpers in the documentation on GitHub. So let's try to launch this updated configuration, the husky titer.launch, and see if we got better. Yeah, before the simulator launches, you have seen that there are the debug, a lot of debug outputs, which are useful when you're setting up the filter, but of course they are taking time to compute. So once you have the filter configured, it's better to turn them off so that you just get the full performance of the filter. So now you can see one of the other debug configurations, that's debug PCL inside. That's the brown point cloud. It's also called LiDAR inside here in the RVS window. And you can actually tell the robot body filter to segment the point cloud, the input point cloud, to 4 segments. The valid points, then there are points that would be clipped because they are too close or too far. We have none here, so you don't see them, but they would be yellow. Then you have the points that are detected as inside the robot body. That's the brown here. And later we will talk also about setting the shadow filter, which would be blue. So you can now see that the point cloud is segmented. I can turn on or off just the points that are on the body of the robot. I can even turn off the valid points and keep just the invalid points that are on the body of the robot. And we can again display the model that is used for the filtering. And now you can see that, for example, on the wheels or on the bumpers, it is really as tight as possible. But on this top link with the sensor rack, it is actually larger. Oh, I got lost. I'm sorry. Yeah, but it is larger. And here is the view. Yeah. And you can see that all the points that we identified as being inside the robot are actually inside the green box of the top rack. And you can see also, maybe, if the colors are not that bad, that we scaled the top link as small as possible to actually cover all of these points, because you see that the LiDAR has a lot of noise here, and that the points really can get about like 5 centimeters off. So this is the way how you can fine-tune the model, increase or decrease the scaling of individual links so that you get as precise filtering as possible. So that would be the simple case. And now let's move on to more complicated stuff. So what, for example, if your robot has some moving parts? A lot of our robots have moving parts. And what if you want to filter multiple point clouds? Because usually robots have more than one source of 3D information, like a LiDAR and a depth camera or something like that. So the good news is that you don't need to do anything to support moving links. They are supported out of the box. If you have the correct URDF collision model, that's all you need to do. And we will show that on the model of the Boston Dynamics Spot robot. And the Boston Dynamics spot also has 5 depth cameras on the body. So we will also show how to configure the multiple point cloud filtering. So basically, unfortunately, the filter framework from ROS doesn't support like one filter to run for multiple point clouds or multiple inputs. They're just single input, single output. So we need to run one filter for each of the, or one filter chain for each of the sensors, as is done here. One laser filter is called laser filter, and it takes the LiDAR points as input. Then we have the TOF back filter that takes the back depth camera points, and so on. You would have like six nodes here, each one for filtering one point cloud. And to ease the configuration so that you don't need 6 configuration YAML files, you can actually, you can move the configuration one level higher. So before, the ROSparam load command was inside the node. But if you want to configure multiple filters at once, you can move it one level up. So at the same level where the nodes are, and add the one more layer here, or one more level. So you can see that the laser filter node has its name mentioned here, and the TOF back filter has its name mentioned here. So this is how you get multiple configurations in one file. And you can see we have configured, again, like just the robot body filter into each of the laser filtering chains. For the LiDAR, it would look basically the same as it did for the Husky robot. There's nothing more specific. Just the links are named differently, and that's all. And the TOF back filter, it's a camera looking backwards. So maybe I'll launch the spot to see how it actually looks. So you can see I have already prepared the spot filter.launch command that starts the simulation of the spot robot. Just be aware that the simulation is pretty slow because it's running less than 10% real time. It's just because of the number of the 3D sensors. And actually, the rear camera on spot can only see the rear legs. You know that there is no way how the rear camera could see the front legs. So just as a way to speed up the filter, we specify the only links argument, which tells the filter that it should ignore all links except those that are listed here. So you know that the back camera filter will only look if the points lie in the rear leg. So here is the spot in the simulator. You can see we painted the spot blue because that's our university color. And you can see the LiDAR in the front. That's the Oster OS0 LiDAR. And then there are the depth cameras on the sides of the robot. And we will see the output in the RViz window. And you can see that the LiDAR, for example, it does see a lot of the robot. So here is some yellow points around the LiDAR. That's the clipped points, the LiDAR clipped. Those are the points that are too near to the sensor. Then the brown ones, which we already know, the points that are detected to lie on the robot body. And you can also see the depth camera output. If I turn it off, you see that this is what the LiDAR does see. And now if I turn off the LiDAR and turn on the depth cameras, yeah, so this is what the depth cameras see. But this is the filtered output with the configuration you have seen. If I turn on the original point clouds, the non-filtered ones, you can see that the rear camera does actually see the legs. And these are the points we, again, wanted to get rid of. I will try to Vogue the spot if that works, because the spot has already some controller running. So I think if you press I, it could try to walk, but it's not really, yeah. So if you press the letter I, the spot will try to walk, but I think I got it too fast. Yeah, poor spot. This does not actually happen to the real one, but the simulation, you know, it's not as perfect as the real spot. But yeah, you can control the spot via the keyboard teleop. The I is for moving forward and M is for moving backward. And you see that as the robot moves its legs, it actually becomes more and more needed to filter these points out. So that's how the robot body filter works here for the spot robot. You can play with it. If you have a gamepad and launch the workspace locally, you can even walk the spot using the gamepad. It's no problem, and it can even do the body dancing moves you saw probably in some advertisement videos of Spot. So go forward, play with the Spot model, and see how it behaves, see what it does. Yeah, there is also an option if you don't have a gamepad, and with the other robots that don't have the keyboard teleop running, you can pass argument fake teleop, which actually replace a back file of commanded velocities that I have recorded for each of the robots. So if you want, for example, to try the husky robot and see how it behaves if it's moving, you just load the husky simple or husky tighter.launch, pass there XLL equals true, and usually it's better to also pass some rate so that the simulator doesn't want to run 100% real time because it's not able to run that fast, but the commands from the fake teleop would be played real time, so that would not really go along very well. So now I launched the simulator with the fake teleop, and if everything works, the robot should start moving in a while. Yeah, you can see it started moving. So this is how you can test actually how does the filter work with a moving robot without having any controller at hand. So let's go on to the third section about shadow filtering. So what are the shadows? Some of you might probably see these shadows on the data they collect on their robots. And the shadows are something that's caused by the physics of the lidars. You know, lidars usually work with some light that's emitted from a point source. And this point source of light gets refracted on edges of objects. So for example, here with the Absolem robot, here is the lidar, the thing in the front of the robot. And the lidar casts the rays to the sides of the robot. And here is a flipper of the robot that has the sharp edge. And the lidar casts the ray here, which would normally miss and measure some point on the back or on the environment, or it would end up on the flipper. But because of the refraction, the lidar actually gets noisy data that can tell it that, for example, a point is measured here, which is like in the middle of nowhere. There's nothing here in the reality, but the lidar sees a point there. And there is a way to get rid of also these points, and that's using the shadow filtering. So before I have told you to switch the shadow filter off because it's more computationally demanding and you need to set it correctly for it to work. So how does it actually do the filtering? It considers each point in the measured point cloud and casts a ray from the point to the lidar or to the sensor generically, and asks whether there is a part of the body through which the ray goes. So for example, for this point, if we again inflate the robot body a bit, if I would connect this point with the lidar, I would see that it intersects the robot body here on the flipper edge. And such points are marked as shadow points. Consequently, from the definition of how does the filter work, it's important to always ignore the link of the sensor itself, because usually you have some collision element also for the sensor. But if you would ask if the point is connected or is intersecting any part of the robot body when you cast the ray to the sensor, it would always intersect the sensor link. So the most important, if you enable shadow filtering, is to ignore the sensor frame. And it would be here, yeah. So here is a configuration for the Marv robot, which is a tracked robot, a little bit different one. It's this robot. It also has tracks, which also cause the shadows, as you can see here. And so the most important thing, if you enable the shadow test, is to exclude the sensor link, or yeah, here's the ignored links in shadow test. This is the most important part. If you don't have that, it would mark all of the points as shadow. You can try that. If you just delete the X1 laser, and you will see that there's nothing left of the point cloud if you don't put the X1 laser here. So again, this is basically everything that's needed to set up the shadow filter, but as the shadow filter basically does ray tracing, it's really required to think about performance, because if you have several million points per second and you have, for example, like 20 links on the robot, and each link might be composed of several more collision elements, you have to basically do ray tracing of this many points against this many collision elements and so on. So the shadow filter is really performance critical, and you should, for example, ignore all the links that you can. Again, the links that you know the LiDAR will, for example, never see. And there is also another important setting, that's the max shadow distance. And this tells that the shadow filter should not work on points that are further than 1 meter from the sensor. Usually the shadow points, as they're defined, are generated just close by to the robot body. So actually limiting the shadow filter to 1 meter from the sensor makes sense. And it saves a lot of computation. For example, with this 128 layer Austral LiDAR, the filter would not be able to run in real time if I would not set the max shadow distance. So
Martin,
yeah.
5 minutes.
Okay. So this is basically what you need to think about when you're setting the shadow filter. So that's performance and ignoring the sensor link. That's it. And here you can also see some even more granular configuration of the model inflating. So now you can see that the filter can actually do 2 types of tests. It can test whether the point lies on the body or if it is a shadow point. And you might want sometimes to scale the links differently for the contains test and for the shadow test. So for example, here you can see that I have specified that there is a link, X1 Mobilicom antenna L. And if I put there the suffix :contains, it means that this padding is actually applied only during the contains test and not during the shadow test. And on the other hand, here I say that in the shadow testing, I don't want to inflate camera 4, which is a camera like this one in the front. And it was, yeah, just experimentally, it seemed to take a lot of points and not bring very much things good for the point cloud, because the camera experimentally verified did not cause any shadowing, but if it was inflated, it was just taking too much points around. So let's see how it looks with the Marv robot. And it seems to be loaded. So here is the Marv robot. And wait for the point clouds to come, and they're here. So now you can see that even the lidar shadow debugging point clouds is there, the blue points, and these are exactly the points that are kind of like on the edge of the robot body, or through which the lidar looks over an edge of the robot body. You can also display it here. So before we were trying to display the model for contains test. That was this one. And there is also the other debug test model. That's the model for shadow test. And you can see that this is the model that's used for testing the shadow points. If I disable the raw robot model, you can see that the lidar has disappeared. That's exactly what I was talking about, that it's needed to ignore the link of the sensor itself. So if I ignore the lidar, so this is the model that's used for filtering the shadow. That's it. Yeah. So if I disable all of these debugging clouds, you will see that what we are left with is the super nice point cloud that actually has no false points that we would consider on the robot or caused by the robot. And this point cloud can be input to any mapper or any other node that processes point clouds. And you can be sure that it's really the best you could get out of the sensor. So that was the third part about shadow filtering. And then I added two bonus parts for which we do not have time here, but you might be interested into looking at them. So the first bonus part is how to work with 2D laser scans, because our previous robots had 2D lidars, and they're still pretty common. So the robot body filter can also work with 2D scans. And there is also a bag file recorded on a real robot, not a simulated one, but on a real one. And if you want to test it, here is the launch file. You need to launch Absalom Real Filter, and it will show you how do the real robot data look. You will see that the noise model is quite different than in the simulation, and you will pretty nicely see the shadow points in this one. And the last bonus part is about computing bounding boxes and bounding spheres. That's because the robot body filter works a lot with the robot model. And these are kind of like byproducts. And it's pretty simple to compute them once you have the robot model loaded and processed. So this is some kind of like byproduct of the filter, which you can enable, and it can publish the actual bounding box or bounding sphere of the robot, which is updated as the parts of the robot are moving. So yeah, there are even some like more granular debugging markers, but basically, yeah, you can see the bounding sphere and the bounding box. These can be nicely used, for example, if you have a path planner that's interested in how large actually the robot is, so that it can estimate if the robot will fit in some like narrow passage. You can actually use these bounding boxes or bounding spheres computed by the robot body filter and pass them along to the path planner or tracker or whatever.
Perfect. Thank you very much, Martin.
Yeah.
Thank you very much. So now it's time for questions for Martin. If you have any questions, you know how to proceed. Go to the questions tab in the conference panel and then put your question there. You can also vote for another question that is already there by somebody else. And also then we'll be asking those questions to Martin here on the mic. Okay, excellent. And amazing the project that you have prepared with so much useful robots already simulated and complex of them, and that people can start using it. And I like it especially, of course, the Ledge one, of course, the one from Boston Dynamics, because it's the most spectacular one.
Yeah.
Yeah, but then let me ask you one question that is the top number one here is, are there any plans to migrate those libraries or those procedures into ROS2?
That might come, but as this is mostly practical for our research, we are still, as you have seen, stuck with ROS Melodic. This year we will probably switch to Noetic, but the switch to ROS2 will still have to wait. So until we actually do the switch at the university, there is little hope that I will have time to actually do the port to ROS2. But of course, it's open source, and I'm really open to any pull requests that would add the ROS2 support. So it will definitely happen, but it will probably not be this year.
This year, okay. Okay, I think that this is a proposal for Alexei Merliakov, because he's the one who asked you the question. So maybe, Alexei, maybe you can go and help on migrating to ROS too. And then we have another question from Sashank Bushang, who says that how efficient is or fast is the algorithm, and I suppose that he's worried about the consumption of resources in the computer of the robot.
So if you set it up correctly, it's almost always capable of working in real time on reasonable frequencies. So, for example, the most demanding was the Australidar, which is 128 by 2000 each scan, and it has the scans output at 10 hertz. So it's something like 2 million. Oh, I won't try to do the computation, but it's like okay. millions points per second. And as I said, if I just set the shadow filtering and did not care about the performance, it was running like 1 hertz. Mm-hmm. So that's not enough. But if you do all the optimizations, like ignoring the links that are not needed to be treated, and setting the shadow filtering maximum distance, then it's quite capable of filtering the whole Australidar scan at 10 hertz on one CPU core.
Mm-hmm. So have you tried this into a car? Because here you have used it on robots that are moving. And what about this? Any data that you can share with us about using this procedure with a car, with a LiDAR, doing 3D around?
Okay. No, we don't have a robotic car, so we have definitely not tested that there. But I see almost no difference between a mobile robot and a car. Yeah. It might be, for example, that the shape of the car doesn't change that much, so it might be really better to do some static masking of the point clouds. In this case, so you would just look at the point cloud. See what points are actually covered by the body of the car, and then just apply this static mask. Could be like booleans telling that, hey, this point is a car point, and this is an environment point. Yeah, so if you really need to go after performance, I would choose this approach instead of the robot body filter for a car. And even for, as we started with the Husky robot, which has no moving parts, it could even be used there with higher performance.
Okay.
But on the other hand, the static masking would not be able to get rid of the shadow points. So you might even consider the robot body filter because of the shadow filtering.
Okay. So I think that you launched a second proposal for the audience right here. Is, hey guys, try it if you have the chance, and report to Martin and provide him some feedback also. He would like to hear.
Yeah, sure.
Okay, one final question. Let me go. Okay, so one very interesting one by Marco Pedretti, that he says, how is this filter going to timestamp the original point cloud? Because imagine that you want to fuse this information with other data, such as an image, which has the same timestamp of the original point cloud.
So the filter does not touch the timestamps, it just passes them along. So the timestamp is retained. It's the same as the one on the input point cloud.
Okay, yes, perfect. So that will be the same point cloud with just the points, without the points that correspond to the body of the and that's it. And then, of course, your processing algorithms will have this data a little bit later.
Yeah, sure, there will be delay.
But the timestamp will be correct, will be the original time when it was taken, not the current one after the processing. Okay. Exactly. Okay, great. Great. So we don't have more time for more questions, but I think that those were very, very interesting ones. So thank you very much, Martin, for your presentation, and see you around the universe.
Yeah, thank you for inviting me.